Welcome to This Explainer. Today, we're actually going to trade the towering skyscrapers and bustling streets for something a little different. We're looking downward. We are going to explore the fascinating, completely unseen world of civil engineering that is happening right beneath your feet. It's this wild world of immense pressure, hyper-precise calculations, and some really clever problem solving. Seriously, think about it for a second. Every single time a massive storm hits, millions, literally millions of gallons of water wash over our concrete cities. If we didn't have a highly calculated, meticulously designed system to whisk all that water away, modern cities simply couldn't exist, period. Yet this entire invisible city of infrastructure is something you and I casually walk over every single day without giving it a second thought.
Okay, let's dive into this. We've got a 5-part underground tour lined up for you today. We'll start with calculating the flow, then designing the hidden network, managing specialized flow, accessing the underground, and we'll wrap up with testing for reliability.
All right, part 1, calculating the flow, predicting the storm. Before anybody even picks up a shovel, engineers have to figure out exactly how much water they're actually dealing with, and the mathematical baseline they usually start with is called the rational method. Now, what's really interesting about this formula is its core assumption. It basically assumes that the duration of the rainfall perfectly matches the time it takes for water from the absolute furthest edge of the catchment area to flow all the way down to the outlet. Engineers call this the time of concentration. It's a very conservative, highly theoretical way to calculate the absolute peak discharge of storm runoff.
But here is where theory crashes into reality. The rational method actually completely fails when you apply it to massive, complex city catchments. Why? Well, mostly because it assumes a rainstorm maintains a constant intensity, and we all know that almost never happens over a long storm. Plus, large areas have all different types of soil, right? Some absorb water way faster than others. The formula also only gives you a single peak number, not a detailed hydrograph showing the flow over time. And finally, just guessing the exact runoff coefficient, like exactly how much water bounces off the pavement versus soaking into the grass, is notoriously tricky. So for the big cities, engineers basically have to toss this simple equation out the window and rely on much more complex modeling.
Moving right along to part 2, designing the hidden network. This is all about the pipes, culverts, and connections.
So the complex math is sorted out. Now engineers move into designing the actual physical infrastructure built to handle that flow. And they constantly face a dilemma here. See, a circular pipe is, well, hydraulically perfect. It offers the absolute least resistance to water flow, which saves a ton of money on extra linings. But what happens when underground headroom is incredibly limited, or when excavating through solid rock is just way too expensive? That's when engineers switch to box culverts. Box culverts can handle massive flows while dramatically squashing the required vertical height and spatial width. It's a brilliant trade-off between hydraulic efficiency and the harsh reality of tight underground real estate.
Okay, time to decode some industry jargon. Matching soffit. It sounds fancy, but this is actually a really critical design rule for preventing floods. Instead of aligning the bottoms of the pipes so the water just flows evenly along the floor, engineers intentionally align the top crowns, or the soffits, of the pipes. Here's why that matters. Imagine a drainage system emptying right into the ocean. The tide rises and actually pushes water backward into the pipes. Now, if you aligned the bottoms of those pipes, a high tide could easily surcharge, which basically means completely flood, the smaller upstream pipes. But by matching the top soffits, engineers ensure that even if that massive outlet pipe is totally flooded by ocean water, the smaller upstream pipes still have breathing room. They maintain a head of pressure to keep pushing the city's stormwater out.
And that same obsessive attention to detail applies to the physical integrity of the network too. Because the earth beneath us, it isn't perfectly solid. It shifts, it settles, and it does so unevenly. If you rigidly connect a brand new drainage system to an older, much heavier main channel, the ground shifting is eventually going to snap that solid concrete right in half. To prevent this, engineers insert a literal short pipe segment right at the connection. It acts just like a hinge, providing this absolutely crucial flexibility if the main channel and the new drains decide to settle at different speeds. It's like a shock absorber for concrete.
And speaking of connections, how exactly do you attach a new side branch to a massive main pipeline? I mean, you could just smash an elliptical hole in the main pipe and mortar a side pipe into it, but that relies way too heavily on perfect workmanship. If that side branch protrudes even a little bit into the main pipe, it dangerously traps rubbish and dirt, completely ruining the hydraulic performance. So instead, engineers heavily prefer using precast wide junctions. These guarantee a smooth, flawless connection every time, even if they're a bit of a headache for contractors to align perfectly down in the trench.
Real quick before we leave the network itself, let's talk materials. For small pipes, anything under 600 millimeters, engineers absolutely love vitrified clay. It's super economical. But clay is brittle, so when it's time to build those massive sewers over 600 millimeters, they have to switch to precast concrete. But there's a catch. Concrete is highly vulnerable to the aggressive chemicals found in sewage, so these giant concrete pipes actually have to be lined with PVC just to protect them.
Which brings us to part 3, managing specialized flow, overcoming obstacles and forces.
So we've got our basic network built, but sometimes standard gravity-fed pipes just aren't going to cut it. Picture this, an underground subway tunnel is sitting squarely in the way of your sewer route. You obviously can't bore straight through it. So engineers use what's called an inverted siphon. It's basically a pipe that dips down into a U-shape right under the obstacle and then comes back up the other side. They're absolute lifesavers for routing, but man, do they come with massive headaches. They cause a serious loss of hydraulic pressure, and worse, that U-shape constantly runs completely full of water, which creates the perfect trap for silt and sediment to just pile up. Unsurprisingly, they are incredibly difficult for workers to access and clean out.
Then we have the sheer immense force of physics to deal with. Have you ever heard of cavitation? It's wild. Based on fluid dynamics, think Bernoulli's equation, when the velocity of fluid gets extremely high, the dynamic pressure actually drops. And if that pressure drops below the saturation point, dissolved gases hidden in the water suddenly release, and they form these little air bubbles. But when that water hits a normal pressure zone again, those bubbles collapse violently and rapidly. This isn't just a little pop. The high-frequency shock waves from cavitation literally chip away at solid concrete and can physically destroy a pipeline from the inside out.
Now, right at the very end of the line, to manage water escaping into the sea, engineers use flap valves. Traditionally, these were these massive, heavy cast iron doors. But cast iron corrodes pretty terribly in seawater. Plus, it's so heavy that it requires a significant amount of built-up water pressure just to push the door open. Today, engineers much prefer high-density polyethylene, or HDP. HDP doesn't rust, it needs practically zero maintenance, and it opens super easily with just a tiny trickle of water. The trade-off? An HDP valve just isn't as physically strong as iron, and it can really only withstand a water column pressure of about 5 meters.
All right, part 4, accessing the underground. Manholes and the humans who maintain them.
Because, let's be real, all this incredible infrastructure is entirely useless if workers can't actually get down there to clean and maintain the system. You've probably stepped on thousands of manhole covers in your life. Traditionally, they were made of cast iron. But cast iron covers are astonishingly heavy. We're talking a massive physical hazard for the workers tasked with lifting them day in and day out. The modern solution is ductile iron. It's much lighter, far less brittle, and significantly safer for the crews. But here's the catch. Because ductile iron is so much lighter, when vehicles drive over them, the covers tend to bounce and rattle, creating a terrible noise. Therefore, these ductile iron covers have to be cleverly designed to interlock firmly with their frames to keep them locked completely tight.
So, the workers pop the cover open, now what? Well, the physical size of the pipe entirely dictates how they actually clean it. For tiny pipes under 300 millimeters, it's straight-up manual labor. Workers literally shove 1-meter rods by hand down the pipe to break up blockages. For mid-sized pipes, they'll hook hoses up to fire hydrants and blast the blockages with pressurized water jets. But for the massive main lines over a meter wide, they have to use heavy-duty mechanical winching. And here is an amazing fact about that. The maximum length of that winching equipment is exactly 120 meters. Because of that hard limit, urban planners are strictly forced to space main street manholes exactly 120 meters apart, or less. The cleaning equipment literally dictates the design of the streets above. Crazy, right?
And finally, part 5, testing for reliability, ensuring the ground holds.
Because once the dirt is finally thrown back over these pipes, fixing a mistake becomes an absolute nightmare. So rigorous quality assurance testing is mandatory. First, engineers test a microscopic structure of the concrete itself using a water absorption test. See, when mixing concrete, you need excess water just to make it workable. But as that water dries out, it leaves behind these tiny little air voids. If there are too many voids, the concrete becomes porous, which practically invites those aggressive wastewater chemicals to seep right in and rot the pipe from the inside out. Testing the water absorption ensures the concrete is dense and impervious enough for a long, healthy lifespan underground.
Next up, they have to prove the entire assembled pipeline doesn't leak. And they basically have two choices here. air tests or water tests. An air test is incredibly fast, it's simple, and it doesn't waste thousands of gallons of drinking water. But if the pressure drops, the air test is totally useless at telling you exactly where the leak actually is. A water test, on the other hand, is slow, it's tedious, but it will perfectly pinpoint the exact joint that's failing. However, remember those tiny concrete voids we just talked about? Sometimes a water test fails not because there's actually a leak, but simply because the porous concrete itself is slowly drinking up the test water.
Our source material actually hits the nail on the head here, noting good quality concrete is characterized by having minimal voids left by excess water, and therefore water absorption test is adopted for checking the quality. This really highlights the meticulous, almost obsessive care engineers have to take with every single variable. They aren't just randomly dropping concrete tubes into the dirt, they are finely balancing chemistry, fluid physics, and heavy machinery to ensure these invisible systems absolutely do not fail us when the big storms arrive.
Well, we've covered a lot of ground today. Actually, scratch that. We've mostly covered a lot underground today. From the sheer mathematical limitations of predicting rainfall to the physics of cavitation to exactly why your local manhole covers don't rattle when you drive over them. The next time you step over a manhole cover or just watch the rain pour down into a street drain, will you see that invisible city working away right beneath you? I really hope this explainer gave you a brand new appreciation for the hidden engineering that makes our modern lives possible. Keep questioning, keep learning, and thanks so much for joining me.